Hello, Honors Chemistry, and welcome to the Chapter 1 and 2 review. So, in the land of things to review, first of all, for Chapter 1, there is very little to actually review, right? Outside of this whole know your element names and symbols, right? Which I assume you know because you guys did a good job on the quiz. Make sure that that's something you review, right? You will be assessed on the spelling, right, of the name and the symbols, okay? And then a couple of other things to go through, right? So what's a conversion factor? Because that's basically the crux of all of Chapter 2, right? And you don't know it yet, but it is the crux of much of what we'll do this year, right? So when we talk about what a conversion factor is simply an equality, right? And when we say equality, what is that going back to math class? Right, that is something where we have an equal sign and both sides are equal. Yes, like both sides have the same weight. Yes, or mean the same thing expressed in a different way, right? So, for example, here are the ones you were supposed to memorize from the outline or the book, right? So, the relationship between kilograms and pounds, right? That is, kilograms are bigger. 1 kilogram is equal to 2.205 pounds, right? Between gallons and liters, right? Gallons are bigger, right? Because if we think about a gallon jug of milk, for example, right? And think about a liter, which would be like 2 normal sized of those disposable water bottles, right? 3.785 liters. If we think about inches to centimeters, again, inches being the bigger one, right? 2.54 centimeters. And kilometers to miles, right? Kilometers are big. Actually, no, I guess that one's backwards and we just say it differently, right? So, for example, when you go out and you run a 5K, right, you're running 5 kilometers, but you're only actually running like 3 and change miles, right? Okay, so anyway, here are those that you were supposed to memorize. Thinking about how this relates to our prefix table, right, because we have to be able to use this. And again, the way I do it in every single example is the exact same way every time because consistency is what leads to reproducibility, which means you're going to do it right out of habit very, very soon in the future, right? If you're always doing it differently, then it's not going to become habit. It's not going to become second nature. And if you're always having to think through how to do a conversion, it's going to get really hard when we start layering on new stuff, right? This foundational stuff has to sink in to the point where it becomes second nature, right? And that's the whole point of what good learning is, right? You repeat it enough times, you emphasize it enough times, right? You apply it, right, which means flip it around and figure out how to do it a different way enough times that it becomes second nature. So when we layer on the new stuff, your brain doesn't have to think through all the old stuff too. Yes? All right, which is why mastery is important and not just I kind of get it. Those are very different things. All right, so anyway, you'll note that on my table, right, you'll see that all of these exponents are positive, and it's designed that way because we're always going to have one big thing and some giant number of small things. And by giant number, we mean positive exponent, yes? So if we wanted to write the relationship between, let's say we wanted to do teragrams and grams, for example, which of these is bigger? The teragram, and tera has a prefix of 12, right? Which means this is going to be 10 to the 12th grams, yes? Let's say we wanted to do the relationship between teragrams and kilograms, right? Again, which of these is the bigger unit? Right, teragrams. Now we find kilo. Kilo is 3. This is 12, which means we're moving 3, 6, 9 places, yes? So 10 to the 9th, because all we're doing is talking about moving the decimals, right? Let's say we wanted to convert between meters and micrometers, right? So again, the bigger unit is going to be the meter, and this will be 10 to the 6th, right? But let's say we wanted to do the relationship between micrometers and attometers. We'd have to find which one's bigger, which would be micro. This is 18, so it's 3, 6, 9, 12. So 10 to the 12th attometers is equal to 1 picometer, yes? Now, let's say we wanted to do across that base unit, right? Where again, the base unit is just anything that doesn't have a prefix on it, right? So that could be meters, it could be grams, it could be liters, it could be seconds. So let's say we wanted to go from picometers to megameters, right? So pico, let's get a different color here. So pico is 12, mega is 6, so it's 6 to the base unit another 12 to get there for a total of 10 to the 18th. Yes, so one big one, 10 to the 18th picos. Yes, and all of those are the conversion factors that we would use for the respective conversions. Yes. All right, let's do a few together. Okay. Oh, actually, no, I forgot. Let's practice counting a few sig figs. So thinking back to our sig fig rules, right? We have 0. Blah, 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 237, right? And again, for a decimal measurement, the significant figures cannot begin, right? Because we're reading left to right. The measurement cannot begin until we get to some actual figures, right? Likewise here, right? Not till we get to some figures, and a 0 embedded in between figures that are significant are clearly significant, right? I don't know how else to say that, right? Same thing, right? 1, 2, 3, 4, 5, 6, right? And this last 0 comes after digits and after decimals, therefore it is significant. Scientific notation is always the easy one. Everything we write is significant, right? Here, the only things that are ever going to be ambiguous are zeros, and that has no zeros, so that one's pretty simple. Here would just be 1 because it's not closed with a decimal, right? Nor does it have zeros following a decimal. Here, right? That one is 3, right? Because again, these zeros serve as placeholders, right? To show you the difference between 345 versus a 34,500, right? Because it's a matter of size. Here again, scientific notation. Here, right? These are zeros embedded between numbers. So 1, 2, 3, 4, 5, 6, 7. All of them are significant. Yes? Makes sense? All right, let's do a few more. All right, so here we have 65 kilograms to grams. So we would come up with that relationship first, right? So kilograms to grams. Which of these is bigger? Right, the kilogram. And the relationship is 10 to the third, which means now we'll just set it up with our given, 65 kilograms. And then we'll fill in our conversion factor, which that needs to cancel, so that goes on the bottom. The kilograms cancel. Now all I have left is grams. And so here, that one's easy enough. We don't even need a calculator. Now, last step is to check significant figures, 2, 2. But what's also not quite right about this answer? Right, we need to adjust that decimal, right? Because if we think about what this is saying, right, there's an implied decimal here, but proper scientific notation says we should move the decimal there, right? Which means that this should this should become 6.5, right? Now, what does that do to that decimal? Or what does that do to the exponent? Well, it means we have to move one place further, yes? If we were supposed to go 3 places from here, now we're tacking on 1 extra place, so times 10 to the 4th grams, yes? And again, if that is hard for you to visualize, right, like if this whole concept of like how to adjust the exponent for moving, what's the simple fix for that? Right. Rewrite this in scientific notation. Just always, right? Because most of you, I would bet, can rewrite that properly, right? As 6.5 times 10 to the first kilograms, right? Super simple. And then you would set this up. From what I can tell, you guys seem to be doing a great job at this, right? And then that becomes really easy, right? Oh, well, this is 6.5. And if I do this, I'm going to add the exponents because I multiply, and then you get the right answer. So anytime you're unsure, or if you feel like this adjusting for proper scientific notation is something that you might struggle with, go ahead and just rewrite your given in proper scientific notation, and that's always going to make your math easier, right? Likewise here, if we take a minute and rewrite that in proper scientific notation, this problem becomes really simple. So let's first get the relationship, right? Milliliters to liters. Which one's bigger? Right. And then this one's going to be 10 to the third. So let's rewrite that. That is 6.6. That's only 2 sig figs, right? Times 10 to the third milliliters. And then I have 10 to the third milliliters for every 1 liter. Oh my gosh, those 10 to the thirds actually cancel. And that's it. Yes, as in now it's easy to visualize the math if you put them in this matching notation, right? All right. What makes M different from the other two? Correct, right? We're talking about cubed units. Now, please always remember when we're talking about these cubed units, right? You will never, right? Take something that's already cubed, right? So you're not going to take this and cube it, okay? This is already a volume, right? This is our given volume. We will not cube that, right? We will cube our conversion factors because our conversion factors as written on here are one-dimensional, right? These are all one-dimensional relationships. So if we want to use them for a three-dimensional conversion, we have to do that work to get it into 3 dimensions, right? So we're going to take our it's unhappy. We will take our 6.0 times 10 to the 9th nanometers cubed. And then we'll come up with our relationship between nanometers and centimeters. So nanometers and centimeters. Which of these is bigger? Right, centis. Centis are 2, nanos are 9, which means this is 10 to the 7th, right? Now, we will cube that, right? And then now that means my nanometers cubes cancel. I still have to apply that here, right? And if I take 7 raised to the 3rd, I get, correct, 21. So I'm going to get, and then what do I do with my exponents when I divide? Right, I'm going to subtract them. So I'm going to get 6.0 times 10 to the negative, right? And here, because we're subtracting 9 minus 21, and that's our final answer, yes? All right, now, a couple last ones here, right? So from yards to kilometers, right? Oh, now, right, this is, we're switching between English and metric, right? So then we got to think through several steps, right? So 599 yards. And again, there are some conversion factors if you want to memorize from the book. There are extras that would make this process faster. Otherwise, you can do it with just the 4 that I said you're required to memorize, right? We know that 1 yard is equal to 36 inches. We know that 1 inch is equal to 2.54 centimeters. And we know that centimeters to kilometers, that's 2. 2 less than the base unit, 3 more, which means 10 to the 5th for every 1, yes? And then it's just a matter of doing the math, right? So what I would recommend, especially if you find that you are setting it up right and then you do the math wrong, then what I would recommend is you multiply across all the numerators, right? So 599 times 36 times 2.54, right? And then we divide by the denominators, right? So then we would go ahead and divide by 1 times 10 to the 5th. And then we'd get our answer, right? Which is why it's important to ballpark your answer and make sure it's reasonable and makes sense. How many sig figs do we need? Right. So 0.548 kilometers. Good. All right, last one. Oh, it's a 2-unit piece. What fun. And remember, so this says milliliters per hour. So it's a flow rate, right? It's about how much volume passes in a given unit of time, right? So 0.5 milliliters per hour, right? And again, per means equal to, right? Should we need it for that? Now, let's start with the hours. So if I need to go from hours to days, right? I need hours to cancel, so it's going to go up here. Do I know the relationship between hours and days? I sure do. And then, now I need to get my mils to gallons, right? Mils to gallons. So milliliters to liters, I know that, right? 10 to the 3rd liters for every 1 gallon. Yeah, you know what I'm saying. And then I know that there are 3.785 liters for every 1 gallon. And gallons per day, yes? And again, multiply across your numerator, right? 0.5 times 24. Oh, we didn't need a calculator for that. Divided by 1,000 times 3.785, which is 3,785. And we get a flow rate of 0.00317. Oh, we only need 1 sig fig, so 0.003 gallons per day. Which makes sense because half a mil per hour is not very much, right? So it makes sense that if we turn it into gallons per day, right, still a very small number. All right. Thank you for listening. Be good and stay tuned for the next review video where we'll do a few of those density problems together. All right, thanks for listening. Be good. Bye.